Question 1.1. Which one of the following compounds has hydrogen bonds between its molecules? So let's go through the options. The CHO tells me that this is an aldehyde. And I know that aldehydes only have dipole interactions. The COO tells me that this is an ester. Esters also only have dipole. The OH tells me that this is an alcohol, and I know alcohols have hydrogen bonds. The COC tells me that this is a ketone, and ketones only have dipole. So the answer to question 1.1, C. Question 1.2, which one of the following is a correct general formula for carboxylic acids? Now, personally, I don't learn the general formula. What I do is I just draw it and then figure out the formula. So, for instance, if I were asked this question, I would draw a carboxylic acid. So a carboxylic acid I could draw would be C, then C, double bond O, and then single bond OH. Then there's going to be a hydrogen here, and a hydrogen here. In this case, the formula is C2H4O2. So this can be simplified as CnH2nO2. And so the answer then is C. Taking a look at question 1.3, study the reactions below. Reaction 1, so you have something, you have H2SO4, and you have a major product and H2O. Then you have reaction 2, compound P, so this product, and then it undergoes hydrogenation and forms compound Q. So which one of the following combinations is the correct IUPAC name of compound P and Q? Now, I want to draw out this reactant, and let's just see what it is. So I'm going to have a carbon, another carbon, a third carbon, and then a fourth carbon. Now the first carbon has 3 hydrogens on it, so hydrogen, hydrogen, hydrogen. The second carbon has 2 hydrogens on it, so a hydrogen and a hydrogen. The third carbon has a hydrogen and an OH. So this is an alcohol, and the last carbon has 3 hydrogens. So the fact that I have an alcohol and I'm using H2SO4 tells me that this is going to be dehydration. I'm going to be removing H2O. So in the H2O, there's an OH and there's a hydrogen. So the OH is definitely going to come out from here. Most certainly it's going to come out from there. But the hydrogen is going to come out either from this, well, it's going to be this hydrogen or this hydrogen. Now we need to remember our rules. Simply put, the hydrogen is removed from the carbon that has the least hydrogens. So if I look at this carbon here, this carbon has 3 hydrogens. This carbon here has 2 hydrogens. So this hydrogen and this OH will be removed to give me my major product. So my product is going to be C, C, double bond C, and then a carbon there. Now I'm going to still have my 3 hydrogens here. I'm going to have 1 hydrogen here, 1 hydrogen here, and then still having my 3 hydrogens like so. So the name of this is but2-ene. And so my options are then going to be B and D. Now to figure out what compound Q is, well, compound Q is formed when compound P, the but2-ene, undergoes hydrogenation. Hydrogenation is simply adding in H2. So I have 2 hydrogens to add, and so because I have a space here and I have a space here, the hydrogens are obviously going to be added there and there, giving me butane. So I'm looking for an option that says but2-ene going to butane, and that's going to be, So but2ene going to butane, that answer is going to be B. Now moving on to question 1.4. The potential energy diagram below is for the following hypothetical chemical reaction. Which one of the following combinations of values for the heat of the reaction, the activation energies can be obtained for this reaction? So from the shape of the graph, we know certainly that the delta H for the forward reaction is going to be negative. Secondly, if I look at the forward reaction, I know that the activation energy here, so this is going to be the activation energy for the forward reaction, and it's going to be less than the activation energy for the reverse reaction, because the reverse reaction's activation energy is going to start here and it's going to go all the way up there. So those three things I can say with certainty. So again, delta H for the forward reaction is going to be less than 0. It's exothermic. The activation energy for the forward reaction is going to be less than the activation energy for the reverse reaction. And so we just need to look for values that match that. So I'm looking for delta H forward being negative. My options are going to be A, B, or D. And then I'm looking for the activation energy for the forward reaction being less than the activation energy for the reverse reaction. And that will correspond with D, because the activation energy for the reverse is 300 and the forward is 100. 300 is greater than 100, and so that works. So the answer there is going to be most certainly D. Taking a look at question 1.5, initially an equal number of moles of hydrogen gas H2 and iodine gas I2 are mixed in a closed container. The reaction reaches equilibrium at constant temperature according to the balanced equation. So which one of the following is always true at equilibrium? Now, I'm going to draw a moles versus time graph here, just so that we can visualize what's going on. So this is going to be moles and this is going to be time. Now, the important bit of information here is that we are starting with an equal number of moles of hydrogen gas and iodine gas. So iodine and hydrogen are starting off with the same value. So those are my reactants. I have some value at the beginning. So most definitely it's going to be somewhere here. Okay? Now, as the reaction progresses, the number of moles of the hydrogen and iodine are going to decrease because they are reactants and reactants decrease. So they are going to decrease like this. Now, because the ratio of hydrogen to iodine is 1 to 1, they are going to decrease by the same amount. So that could be for hydrogen, that could be for iodine. So hydrogen and iodine. Okay? Now on the other hand, we have the product, which is HI. HI is going to start from 0 and it's going to increase to some value. We don't really care what that is. But it's going to be, when these lines are now parallel, that's where equilibrium is going to be reached. So because they started off at the same amount and because they are in a ratio of 1 to 1, the equilibrium amounts of H2 and I2 are going to be the same, and because it's in some container, their concentrations are going to be same. So the answer to this question is going to be A. The concentration of H2 is going to equal the concentration of I2. Now let's take a look at question 1.6. 1.6 says, consider the following reaction at equilibrium. SO2 plus O2 gives us 2SO3. Delta H is negative. Which one of the following changes to the reaction conditions below will increase the yield of SO3? So first one, addition of O2. So let's take a look. If I add O2, now this is at equilibrium, so Le Chatelier's principle will apply. The system will want to decrease the amount of O2 by favoring the side that will use it up. So in other words, the forward reaction is going to be favored. So as a result, the amount of O2 will decrease, but because the forward reaction is favored, the amount of SO3 will increase. And that's actually what we want. So the answer here, quite simply, is going to be A. Now taking a look at question 1.7, the table below shows the ionization constants Ka for two acids at 25 degrees Celsius. Okay, so butanoic acid and an ethanoic acid. Consider the following statements of these two acids when they have equal concentrations at 25 degrees Celsius. So, first one, both are weak acids. So, is this true? The answer is yes, they are true. Well, that statement is true. And the reason is because the Ka values are low. So, low Ka values means weak acids. Okay? The second point, butanoic acid is a stronger acid than ethanoic acid. Now, if we look at the Ka values, ethanoic acid has a higher Ka value than butanoic acid. So it's actually the other way around. The higher the Ka value, the stronger the acid. So because ethanoic acid has a higher Ka, ethanoic acid is going to be stronger than butanoic acid. So that statement 2 is incorrect. Statement 3, the butanoic acid solution has a lower concentration of hydronium ions than the ethanoic acid solution. This statement is going to be true because if you have a low Ka, you have low H or very little H3O plus that's going to form. So you're going to have a low concentration of H3O plus forming. So the only two statements that are correct are 1 and 3. So that answer is going to be B only. Moving on to question 1.8. Which one of the following pairs of acids and bases, all of the same concentration, react to give the highest pH at the equivalence point in a titration at 25 degrees Celsius? So HCl is a strong acid and NH3 is a weak base. That means I'm going to have an acidic salt. HCl is a strong acid. NaOH is a strong base. And so I'm going to get a neutral salt here. HNO3 is a strong acid and KOH is a strong base. And here I'm going to get a neutral salt again. CH3COOH is a weak acid and NaOH is a strong base. This is going to give me a basic salt. Now, the highest pH, if we think of the pH scale, you have 7 in the middle, which is neutral. Then you have these values on the right of 7, which is basic. And on the left of 7 is acidic. So 0 here and 14 here. So if something is basic, it's going to have a high pH, and so the answer is going to be D. Moving on to question 1.9, a galvanic cell is set up as shown below. You have CD and AG electrodes. The question asks which one of the following combinations of the metal used as cathode and electron flow direction is correct. Now, electrons will flow from the anode to the cathode. So in order to figure out which is the anode and the cathode, we look at table 4b. So according to table 4b, CD is higher up. And because it's higher up, it's going to undergo oxidation. And remember that oxidation occurs at the anode. That means Ag is going to be the cathode. So we are looking for the answer that says Ag is a cathode, so B or D, and electrons are going to flow from CD to Ag. So the answer is going to be B. Question 1.10, an electrolytic cell is set up to electroplate an iron rod with nickel, as shown below. Consider the following statements. The iron rod is the negative electrode. Point 2, the metal ions in the solution undergo reduction. Point 3, the anode is pure nickel. So whenever you are electroplating, there's a few important things to remember. The thing that you want to coat, so the thing that is going to be coated, you are coating the cathode. So whatever it is that you are coating, that's going to be at the cathode. So we are coating an iron rod with nickel. So it means that the iron rod is going to be the cathode. Further, during in electrolytic cells, the cathode is the negative electrode. So the iron rod is going to be the negative electrode and it's going to be the cathode. That means the nickel must be the anode, and then therefore it must be the positive electrode. So checking the statements here, the iron rod is the negative electrode. That is correct. The metal ions in the solution undergo reduction. So the metal ions that are going to be in the solution are going to be nickel. So they are going to undergo reduction. They're going to gain electrons. That is true. So point 3, the anode is pure nickel. The anode is pure nickel. That is also true. So all three are correct. The answer is D. So let's now take a look at question number 2. The letters A to H in the table below represent organic compounds. Question 2.1, write down the letter that represents each of the following and alcohol. So A is not an alcohol, A is an aldehyde, and that's because of this group called a 4-mile group. B is a haloalkane because it's an alkane and it has bromines attached to it. C ends in -one, so that's a ketone. D has a single O, so it could be an alcohol. E, E looks like, because of the CCC, that sequence tells me that it's gonna consist of a double or triple bond, and so that gives me an indication. Because of the CCC, I recognize that as an alkyne. F, I have COO. So this could be either a carboxylic acid. No, it can't be a carboxylic acid. It's got to be an ester. So F is definitely going to be an ester. If it was a carboxylic acid, you'll see COOH at the end. G, we have C4H8O2. Now, because of the formula being written like this, it could be a carboxylic acid or it could be an ester. So we're not too sure as yet. And then H, because of the way this is written, you have CH3, C, and then CH3, 2. So this is going to be an alkane. Okay, so question 2.1.1, which one is going to be an alcohol? The only option is going to be D because that only has a single O. So the answer there is D. So D. Question 2.1.2, a compound with a 4-mile group, that's A. 2.1.3, an unsaturated compound, unsaturated alkyne, the answer is going to be E. Question 2.2.1, write down the IUPAC name of B. So B is a haloalkane, so we need to find the longest branch. Now the longest branch is going to be this branch right here. I have a bromine and a bromine here, so that's on carbon 1, 2, and 3. Then I have a methyl and a methyl on carbon 4 there. So this is going to be 3, 3 dash dibromo dash 4, 4 dash dimethyl, and then I can't fit it, so I'm going to write it below. This is going to be 6 carbons, and that's going to be hexane. Question 2.2.2, write down the IUPAC name of E. So E is an alkyne. So it would be easier if we just draw it. So let's draw it first and then we can figure out its name. So I'm going to have a carbon with 3 hydrogens, like so. Then I'm going to have another carbon, followed by a CH3 and then a CH3. Then followed by a carbon, another carbon, and then a carbon that's bonded to 3 hydrogens. Now that means that there must be 3 bonds there. So 1, 2, 3. So in order to name this, I'm going to go in this direction. So that's going to be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So this is going to be called 4, 4, because I have 2 methyl groups there, dash dimethyl, right? Then pent, because there's 5 carbons. I have a triple bond on carbon 2, so pent 2, and because it's an alkyne, it's ine. Now moving on to question 2.3.1, 2 different compounds in the above table are functional isomers. So remember, functional isomers, they have the same functional group, but just different arrangement or structures of it. So define functional isomer, we find out that. 2.3.2, write down the letters that represent these functional isomers. So it's important for us to remember that the functional isomer of an aldehyde is a ketone and vice versa. And the functional isomer of an ester is a carboxylic acid. So we have an aldehyde. The aldehyde is A, and we have the ester, we have the ketone is going to be C. But we just need to make sure that they have the same number of carbons, otherwise they're not really going to be. Remember, for a functional isomer, they have the same functional group, different arrangement, but they also need to have the same molecular formula. So butanone has 4 carbons, and A has 1, 2, 3, 4 carbons as well. So the answer is going to be A and C. Now, moving on to question 2.4.1. Compound F is formed when a carboxylic acid reacts with another organic compound X. So F is the ester, okay? Write down the name or formula of the catalyst. So to form an ester, that's esterification, you need H2SO4. Question 2.4.2, the type of reaction, it is esterification. Then 2.4.3, the structural formula of compound F. So compound F, they want us to essentially draw it. So I'm going to have a carbon here with 3 hydrogens, then another carbon, then double bond O, then single bond O, and then I'm going to have a carbon with 2 hydrogens, and then followed by another carbon with 2 hydrogens, and then a carbon with 3 hydrogens. And that's my structural formula. Question 2.4.4, they're asking us to write the name of this compound. So what we look for is something called co-co bonds. So CO, so co-co bonds. So this first co, this here, so this entire part of this molecule comes from the alcohol. And then this entire part of the molecule will come from the carboxylic acid. So when we are looking to name compound X, remember compound X is, so they tell us compound F is formed when a carboxylic acid, so we're not looking to name the carboxylic acid, we're looking to name the alcohol. So compound X is certainly going to be an alcohol. When we want to name an alcohol that has 1, 2, 3 carbons, and you have an OH at the on the first carbon. So essentially it's going to be propan, because 3 carbons and then 1 ol. So remember, for esterification we use primary carbons, primary alcohols. Now moving on to question number 3. The vapor pressure of different organic compounds are determined at 20 degrees Celsius. The vapor pressures of compound A, B, and C are not drawn in the table. 3.1 we leave out. Question 3.2, the vapor pressure of compounds A, B, and C are given in random order. 3.2.1, write down the vapor pressure of compound C. So in order to figure out what compound C is, we need to think about what what are they changing in each compound. So A, B, and C, you have pentane, you have 2-methylbutane, and C is 2,2-dimethylpropane. So essentially what they're doing is they are increasing the branches. So C is the most branched. And because it's the most branched, we know that it's going to have the weakest intermolecular force. And so it's going to have the lowest boiling point. And we know that boiling point, the lower the boiling point, the higher the vapor pressure. So if C is going to have the lowest boiling point, it's going to have the highest vapor pressure. So that means the vapor pressure is going to be 146 kPa. Question 3.2.2, explain. Okay, we've explained it. Moving on to question 3.3, compounds D and E are compared. So D and E, so we're dealing with D's. Which compound has the lower boiling point? So low boiling point, low BP means high vapor pressure. Now if I look at these two, E has a high vapor pressure. That means it's going to have a low boiling point. So the answer is going to be E. Question 3.3.2, explain the difference in vapor pressure between compound D and E. So D is propanoic acid. So D is a carboxylic acid. And carboxylic acids have hydrogen bonds, which are strong. E, on the other hand, is an aldehyde. It ends in al, Al. So it means it's an aldehyde. Aldehydes have dipole-dipole interactions. And it is weaker, those are weaker than hydrogen bonds. And so because of that, E is going to have a weaker intermolecular force and it's going to have a lower boiling point. Now moving on to question number 4, which are reactions. Study the flow diagram below. Reaction 1 is a cracking reaction forming two organic compounds, W and T, as the only products. So we have this flow diagram that looks kind of hectic, and they're asking us to define a cracking reaction, and then we leave that out. Let's move to 4.2. So 4.2 is the product in reaction 2. So in this reaction here, a primary, secondary, or tertiary haloalkane, and then give a reason. So this is quite straightforward because it's going to be a primary because the bromine is attached to a carbon that's only attached to one other carbon. So the bromine is attached to a carbon that's attached to only one carbon. Okay, question 4.3. Write down the structural formula of compound W. Now, compound W is going to be this organic compound. Okay, so to figure this out first, we need to figure out whether that's going to be an alkane or it's going to be an alkene. So the trick here is to look at the products of the cracking reaction. So any cracking reaction, so cracking, you are going to form an alkene and you are going to form an alkane. Now I know one of the products. One of the products is C4H8. C4H8 is the general formula for an alkene. So this is an alkene. So that means that this must be an alkane. Right? Not a haloalkane, just a simple alkane. So reaction 2 produces a haloalkane, which means W must be the alkane version of that without the halogen. So simply it's going to be 1, 2, 3, 4 carbons, and it's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogen. Now the next question, 4.3.2 says, write down the molecular formula of compound U. So compound U is the original compound at the beginning. So this is going to be quite a simple one, because to figure out what compound U is, it's simply going to be the sum of compound T and compound W. Compound W, we know, we just did it now, so it's C4H10. So C4H10 plus compound T is C4H8. And if I add them up, I'm going to get C8H18, and this must be the molecular formula for compound U. Now, let's move on to question 4.4. For reaction 2, write down the name or formula of the inorganic reactant. So here, if you are going from an alkane to a haloalkane, what is the inorganic reactant? So that's going to be, to 4.4.1, we are going to be using Br2. Question 4.4.2, what type of reaction is this? So if it's an alkane, I call it a 1 because it's got all single bonds. And if it's going to a haloalkane, that also only have single bonds. So that's also going to be a 1. So if it's going from a 1 to a 1, that must be a substitution reaction. Question 4.4.3, one reaction condition. So for this to occur, we need UV light. Let's move on now to the next part of the question, question 4.5. So question 4.5 asks, write down the type of elimination reaction in reaction 3. So reaction 3, we are going from a haloalkane. So haloalkane, and we are going to organic compound R. So we don't know what that is, but we know it's an elimination reaction. So that means we are going from a 1 to a 2. We are going from an alkane, or a haloalkane in this case, to an alkene. Now the only type of reaction that a haloalkene will undergo to become an alkene is going to be the one that removes that halogen. So that's going to be called dehydrohalogenation. Now let's take a look at question 4.6. So question 4.6 says compounds R and T are positional isomers. Okay, the inorganic reactants shown below are available for reactions 4 and 5. So we've been given this list. Question 4.6.1 says write down the balanced equation for reaction 4 using structural formulae and the correct inorganic reagent shown above. So for 4.6.1, we know certainly that compound R is going to be an alkene. So let's draw that in. It's going to have 4 carbons, 1, 2, 3, and 4. So 1, 2, 3, and 4. Remember, compound R was the product of a dehydrohalogenation reaction. So in other words, the halogen, the Br, and a hydrogen would have been removed. So the double bond would have formed here. Now let's fill in our hydrogens. So hydrogens will go everywhere else like this. And we'll add 1 and 2 there. Now, because we are going from a 2, an alkene, there's only one type of reaction that goes from a 2 to a 1, and that's an addition reaction. So reaction 4 is most certainly going to be an addition reaction. Now, using the reagents that are here, the one that's going to help us with an addition reaction is going to be HBr, because the HBr is going to do 2 things. It's going to first break the double bond, and it's going to substitute a hydrogen and a bromine on it. So I'm going to add in here HBr. Now when we're looking at our products, we're going to still have a 4-carbon parent chain. So here's the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. But now, because we are doing an addition reaction,
we're going to add in a hydrogen and a bromine. So remember, during an addition reaction, the hydrogen is going to go to the carbon that has the most hydrogens. So this has the most hydrogens, and so that's where this new hydrogen is going to go. And the bromine is then going to occupy this space right here. So 4.6.1, the balanced equation, structural formula, correct inorganic reactant or reagent shown above, that's going to be our solution. Now question 4.6.2, write down the balanced equation for reaction 5 using structural formulae and the correct reagent. So reaction 5 is using organic compound S and is going to organic compound T. So let's draw that in. So we know what S is. 1, 2, 3, 4. We've got a bromine here. We've got the hydrogen here. And there's hydrogens everywhere else. Like so. Okay, and now we are adding in something, and then we are going to form C4H8. Now, what we're going to do here is we are going from a 1, which is an alkene, and we are going to a 2, which is an alkene. So an alkane to an alkene. So a 1 to a 2. So this is going to be an elimination reaction. So reaction 5 is simply going to be an elimination reaction. Now, elimination reactions form, they form alkenes and they form double bonds. So we need to pick an appropriate reagent here. And the reagent we're going to use is going to be NaOH. So NaOH is going to do two things. Firstly, it's going to take out a hydrogen, and that's going to allow us to make the double bond, and it's going to remove the bromine. So our products here are going to be, so this the 4 carbon chain like so. Then we're going to have hydrogen, 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 hydrogen here. Now there's still going to be a hydrogen here, and we got the bromine. So the bromine certainly is going to be removed. So this is going to be removed. So let's take that out. So we've got this vacant spot. Okay, so we've got this. Now, is this hydrogen going to be removed, or is this hydrogen going to be removed? The rule is the one with the least amount of hydrogens is going to be removed. So this one, this carbon has 1, 2 hydrogens. This carbon has 1, 2, 3 hydrogens. And so this is going to be the hydrogen that's removed. So our product is going to have a double bond that's formed here. And some of the byproducts are going to be Na, and it's going to have taken the bromine, so NaBr, and then the OH is going to take the water, so you're going to have H2O. Let me just write that a bit better. So H2O. And then the last question, write down the IUPAC name of compound T. This is compound T. So compound T is simply going to be butene.
Question 5 of this paper says, the reaction between pure aluminium and excess hydrochloric acid is used to investigate the factors that affect the rate of a reaction. The balance equation is given. Question 5.1.1 we'll leave out. Then they tell us experiment 1 uses 1 mole per dm cubed HCl, and it reacts with 0.5 grams of aluminium strip from an aluminium roll at room temperature. The graph of volume versus time for this experiment not drawn to scale is shown below. Question 5.1.2, they tell us for the time interval 0 to 5, the rate of the reaction or the rate of formation of H2 is 0,033 dm cube per minute. Calculate the mass of aluminium present in the container at 5 minutes. Take the molar gas volume as 24,5 dm cubed per mole. So for 5.1.2, we'll start off by using the rate formula. So rate is equal to the change in the volume divided by the change in the time. Now, basically, it's the gradient. So the rate is given as 0,033, and that's equal to but we don't know what this volume is, so let's just call it VF. So VF divided by, and here it's going to be 5. So we cross multiply, you get VF is equal to 0,165 dm cubed of H2 formed. Now we've been given the molar gas volume, so we can then convert this to moles. The number of moles is equal to the volume divided by the molar volume. So 0,165 divided by 24,5, and that's equal to 6,73 times 10 to the minus 3 moles. And again, this is of H2. Now we are asked about aluminium, and we have H2, so we can do a mole ratio. To get the number of moles of aluminium that was used, that's going to equal 2/3, so 2/3, because of the ratio 2 to 3, of the number of moles of hydrogen. So 6,73 times 10 to the minus 3. And that's going to equal 4,49 times 10 to the minus 3 moles of aluminium used. Now we can convert this to mass. So the mass of aluminium that was used is equal to the number of moles, so 4,49 times 10 to the minus 3, multiplied by the molar mass from the periodic table is 27, and that's equal to 0,12 grams used. The question is asking about the aluminium left over, so the amount of aluminium that's left is going to equal the amount we started with, which is 0,5 minus how much we used, 0,12, and that gives us 0,38 grams that is left over. Question 5.1.3, assume the concentration of the H2 stays constant for the duration of the reaction. Use collision theory to explain the change in the reaction rate from T0 to T5. So I'm going to write it in point form, but basically at the beginning of the reaction, we have a large surface area of aluminium. So you have an increased surface area. Now, because you have an increased surface area, you're going to have a high rate. But as the reaction continues, right? So as reaction proceeds, the surface area decreases because, of course, you have less and less, or fewer and fewer points for reaction to occur. So you're going to have fewer effective collisions per unit time, and as a result you're going to have a decreased rate as time passes. Now question 5.1.4, experiment 1 is repeated using a 2 mole per dm cubed solution. Redraw your answer, or redraw the above graph and label it. So I'm just going to draw it on here. So if we use a higher concentration, at the beginning we used, in experiment 1 we used 1. So if you use a higher concentration, you essentially have more moles, more particles, more effective collisions, higher rate. Now, because the HCl, so they tell us here at the beginning, the HCl is in excess. So the amount of product that's formed is not going to be dictated by the amount of HCl. So even though we have more, we're still going to be producing the same amount of hydrogen gas at the end. So the reaction rate, or the graph is rather, the graph rather is going to look something like this. So it's going to be quite steep, and it's going to flatten out much sooner. So that's reaction 2. And moving on, experiment 3. Experiment 1 is repeated using 0.5 grams of pure powdered aluminium. So how will the volume of H2 produced in reaction 3 compare? So by using powdered aluminium, the amount of H2 that's produced is not going to change. It's going to remain the same. The only thing that's going to change is the rate of the reaction, because now you have a larger surface area. If it's powdered, it's going to be a larger surface area. Now moving on to question 5.2, curve X is the Maxwell-Boltzmann distribution curve for a reaction under a set of reaction conditions. A change was made, and so we have curve Y. So 5.2.1, what change was made? They increased the temperature. And question 5.2.2 is asking us to explain why. And it's simply because if we examine this graph, on the x-axis we have kinetic energy. And we know that temperature and kinetic energy are directly related. So if you look at the peak here and the peak here, the peak has shifted to a higher kinetic energy value. So this was the original, some value here, and now the peak has shifted here. So it has shifted to a higher value. And so it means that because it's shifted, it's going to be at a higher temperature.
The reaction of carbon monoxide with oxygen as investigated, or is investigated rather. The reaction reaches equilibrium in a closed container at constant temperature T. They give us the reaction and they tell us that delta H is less than 0. Changes to the conditions of equilibrium are made at different times. The graph shows the results obtained. X, Y, and Z represent the gases in the above reaction. Alright, now we can see that on our x-axis we have different time intervals, T1, T2, T3, with some changes happening at each interval. On our y-axis we have concentration, so we are measuring the change in the concentration as time passes. The question reads, use the graph to answer the question. So at T1, oxygen was added to the container. Write down the letter that represents O2, choose from X, Y, or Z. Alright, so at T1, so T1 right here, we are looking for, so if something is added, we are looking for a sharp spike. Alright, now the one that has a sharp spike is X. And the reason why you would get a sharp spike is because something is added. There is an immediate increase in its concentration. Okay, so the answer to that O2 is going to be X. So that's going to be my graph for O2. Next question reads, at T2, the pressure is adjusted by changing the volume of the container. Was the pressure increased or decreased? Okay, now at T2, let's just make a note of what's happening. So at T2, I can see on this graph, or on these graphs, that okay, there's a decrease in these concentrations. Okay, so there's a decrease in the concentration. So nothing I can read too much into it that much, or so far. However, afterward, there's some changes, and that's what we should focus on here. We'll notice, and let's just track the oxygen graph, because we know it's oxygen. So oxygen decreased sharply, and then it had a gradual increase. Right? It had a gradual increase, which means that if I wrote this reaction, 2CO plus O2 gives me 2CO2. Since the oxygen curve is increasing, it means that the side that oxygen on was favored. In other words, it means that the reverse reaction is favored. Now we need to work backward now, right? So why would the reverse reaction be favored? Or what does the reverse reaction represent? Now when we talk about pressure, we talk about the number of molecules. Okay? Now the reverse reaction represents more molecules. Remember, this side has 3 molecules, this side only has 2 molecules. So in other words, we can say that if the reverse reaction was favored, it means that the side with more molecules was favored. Now, why would the side with more molecules be favored? Well, it must be if the pressure was decreased. So the answer here is that the pressure was decreased. Now let's go step by step through Le Chatelier's principle to make sure that our answer is correct. If the pressure is decreased, the system would want to increase the pressure. How would the system increase the pressure? By favoring the side that has more molecules. In this case, the reverse reaction will be favored because the reverse reaction had more molecules. And so O2 would increase. But not only O2, there's also another molecule that would also increase, CO. Now, we can do two things at once here. If we look at our graphs, we can see that there is another graph that also increased. So Z must be CO. So Z must be CO. And then by process of elimination, it means that Y must be CO2. Again, why am I saying this? I'm saying because since the reverse reaction was favored, the concentration of O2 and CO would increase. Since we know that X is O2, it must mean that Z is CO, since we can see that the concentration increased. Okay, 6.1.5, write down the name or formula of the gas that is represented by Z. Okay, we've answered that. Give a reason, we've answered that. 6.1.7, what change in temperature is made at T3? Choose between increased or decreased. Okay, now let's look at what happened. At T3, I can see that CO2 increased. CO2 increased. Now, CO2, let me write the reaction one more time. So CO plus O2 gives me 2CO2. And now when we talk about temperature, we need to look at the delta H. And the delta H was less than 0. Now, since we can see clearly that the concentration of CO2 increased, it means that the forward reaction was favored. And the forward reaction is exothermic. And the only time an exothermic reaction will be favored is if the temperature is decreased. Right? If the temperature is decreased, then the exothermic reaction will be favored. So the answer here, since the exothermic reaction is favored, it means that the temperature must have decreased. Okay? Use Le Chatelier's principle to explain the answer. We can say a decrease in temperature favors the exothermic reaction. The exothermic reaction is the forward reaction. The forward reaction is therefore favored. Right? That means the concentration of CO2 will increase and the concentration of O2 and CO will decrease. And that's exactly what we observe if you look at those other two curves, they decrease. Okay, let's move on. Now we have our 9-mark KC question. Okay, and the question reads, carbon monoxide gas reacts with water vapor at T degrees Celsius. The reaction reaches chemical equilibrium according to the balanced equation. Initially, 0.6 moles of CO, 0.6 moles of H2O, 0.1 moles of carbon dioxide, and 0.1 moles of hydrogen were mixed and sealed in a 2 dm cubed flask. If the equilibrium constant for this reaction is 4, calculate the mass of CO present in the flask at equilibrium. Okay, now with any KC question, you can get a lot of marks just by constructing the table and filling in certain values. Now the table is a rice table. I mentioned this in previous videos, you can watch them. So what we'll do is we'll construct this rice table. R, I, C, E. Now R stands for ratio, I is initial, C is change, and E is equilibrium. Okay, now let's write out our reaction here. So CO, then H2O, then CO2, then H2. Now I'm going to draw a double line here to separate reactants and products, and then let's just neaten up this table. Now when we talk about ratio, we are talking about the coefficients of these compounds. Now in the balanced reaction they give us, you can see that it's all 1 to 1 to 1. So simple here, the ratio is 1 to 1 to 1 to 1. Now initial represents how much how much was added at the beginning. So at the beginning they tell us you have 0.6 moles of CO, you have 0.6 moles of H2O, you have 0.1 moles of CO2, and you have 0.1 moles of H2. Then they tell us the Kc value. Okay, or they also tell us the volume. So let's write your volume is 2 dm cubed. Okay, next we look at the Kc. Now the Kc, remember, is equal to the concentration of products divided by the concentration of reactants, and the exponents would be the coefficients. So Kc is going to equal the concentration of H2. The coefficient is 1, so we don't need to include it. Then multiplied by CO2, coefficient 1, we don't need to include it. And then divided by CO, and then lastly H2O. Now that is equal to 4. And now all we need to do really is do some calculations here. Now let's go back to our table. We don't know anything about the equilibrium value yet, but we can start filling in the change. Now they haven't told us what it changes by, but we can always use X, right? Now since CO and H2O are reactants, they're going to be used up. So their change is going to be negative. So the change is going to be minus X. And since the ratio is all 1 to 1 to 1, H2O is also going to decrease by minus X. CO2 and H2 are products. So products will increase as the reaction progresses. So they're going to increase by plus X, and H2 will increase by plus X. That means at equilibrium, we're going to have 0.6 minus X. Here is going to be 0.6 minus X. Here is going to be 0.1 plus X. And then here is going to be 0.1 plus X. Don't forget, this is moles. Right? Now, for Kc, we need concentration. And so we can add one more column, or one more row rather, which would be our concentration row. So if we want the concentration here, we just divide by 2. So each one is going to be divided by 2. 0.6 minus X divided by 2. Here 0.6 minus X divided by 2. 0.1 plus X divided by 2. 0.1 plus X divided by 2. Now we have all the concentrations. In terms of X, we can substitute it into our Kc formula. So here we're going to have 0.1, let's use a round bracket rather, 0.1 plus X divided by 2, 0.1 plus X divided by 2, and here 0.6 minus X divided by 2 multiplied by 0.6 minus X divided by 2. And now you can substitute this in your calculator and solve for X. So X will give you 0.37, and this represents the change. So this X value right here is these X values right here. Now remember, the question is asking us to calculate the mass of CO present in the flask at equilibrium. So if we focus on CO, so here's CO, this is the initial, this is how much it changed by, this is the equilibrium moles. So to calculate the equilibrium moles, we can say it's going to be the equilibrium moles is going to be 0,6 minus 0,37, and that is equal to 0,23 moles of CO at equilibrium. But the question is asking to calculate the mass of CO. Now, if we have the number of moles, we can calculate the mass. Remember, number of moles is equal to mass divided by molar mass. We got the number of moles, 0,23, is equal to the mass, that's what we want, and the molar mass is what we get from the periodic table. The molar mass is going to be 28. Now cross multiply, we get a mass of 6,44 grams of CO at equilibrium.
Hydrated potassium carbonate K2CO3.X H2O is a weak base. A solution is prepared by dissolving some of the solid in water. We leave out 7.1. 7.2 reads, write down the formula of the conjugate acid of the carbonate. So if you have been given something like the CO3 2-, and you want to figure out what the conjugate acid of that is going to be, remember an acid simply has one extra proton, or in other words, one extra H. So all we got to do is we're going to add one H to it and change the oxidation number. So CO3 2-, we're going to add an H to it. It's going to become HCO3, and 2- becomes 1-, and that's our answer. So just remember that if you want the acid of something, add a proton and add 1 to the oxidation number. If you want the base, remove a proton and -1 from the oxidation number. Moving on, a hydrochloric acid solution, HCl, of concentration 0.1 moles per dm cubed is titrated with the prepared potassium carbonate solution of unknown concentration. The balanced equation of the reaction is, so K2CO3 plus 2HCl gives you 2KCl plus CO2 plus H2O. The results of the titration are given below. So 7.3 says determine the value of P and Q. So that's this value here and this value here. Now it can be a bit confusing if you don't know how a burette works, because a burette is set up like this. So you basically have like a tube like this, and you have the numbers starting at the top. And as you are dispensing liquid, the level decreases. So what they are saying is the initial reading is 6.5, right? And it stops at P. So the numbers increase as you go down. So we want to know what P is, and they tell us the volume used. So from here to here is 20.05. So if you want to know what P is going to equal 6.5 plus 20.05, which is 26.55. And likewise for Q, if you draw another burette here, so we are starting at Q, we don't know what Q is, and we know we are ending at 48.3. We know the volume that was dispensed, so from here to here is 20.15. If you want to know what Q is going to equal 48.3 minus 20.15, which is equal to 28.13. And this is cm cubed, and that is cm 15, not 13, 15 cm cubed. Let me just neaten that up. So 28.15. Okay. So 7.4, methyl orange is used as an indicator. Explain why methyl orange is used, or why is it the most suitable indicator. So if you look at the reaction, HCl is a strong acid, and KCO3, they tell us it is a weak base. So a weak base and a strong acid will give us a salt that is acidic. So we're going to have an acidic salt. So what we're going to need is we are going to need to use an indicator that is sensitive to pH ranges that are acidic, and that is methyl orange. So methyl orange is sensitive to pHs that are less than 7. And we need that because we expect our salt that's forming to be acidic. Question 7.5, calculate the concentration of the K2CO3 solution. So what we're going to do here is we're going to use our acid-base titration formula, which is CAVA over CBVB equals Na over Nb. Now the concentration of the acid was given to us. It was 0.1. The volume of the acid is given to us here. It is 25. Now when you use this formula, you don't need to convert to dm cubed. So that's the beauty of this formula. Then Cb is what we want. The volume of the base. Now if you notice, we have two different volumes. So what do? We take the average. So the average volume is going to be 20.05 plus 20.15 divided by 2, which is 20.1. So 20.1 goes here. And then Na over Nb, that's straight from our reaction, our chemical reaction. So H, the acid is 2 and the base is 1. It is the mole ratio. And now you can solve for Cb. So Cb is equal to 0.062 moles per dm cubed. Now let's move on to the last question. The above K2CO3 solution used in the reaction was prepared by completely dissolving 6.525 grams of the hydrated potassium carbonate in 600 cm cubed of water. Calculate the value of X. So they want to know what is X here. So what do we know about this solution at the start? Well, we know its concentration. We just worked out the concentration. So the concentration of this is 0.062. We know the mass, and so we can work out the molar mass. And we also know the volume. So we know the volume. So we can work out the molar mass. So the formula that we can use is going to be C is equal to M over capital M times V. So the concentration 0.062 is equal to the mass, which was 6,525. So 6.525 divided by the molar mass. We don't know because remember the molar mass includes the water. We don't know the number of waters, and so we don't know the molar mass. And in the volume, it was made in a 0.6 dm cubed amount of liquid. So we can solve for M, the molar mass. So the molar mass is equal to 174.84 grams per mole. Now we can use this to calculate how many waters there were if we start subtracting the different things. So for example, we know that potassium has a mass of 39. So K2CO3 dot XH2O, the mass of that is 174.84. So potassium is 39, we have 2 of them, plus carbon is 12, we have 1, plus 3 oxygens, and each one is 16, plus we don't know how many waters there are, but each water has a mass of 18, and that's equal to 174.84. Now we can solve for X. X is equal to 2. And so there are 2 water molecules attached to the K2CO3.
So question 8 reads, dilute hydrochloric acid, HCl, reacts with magnesium at 25 degrees Celsius according to the balanced equation given below. So they've given us the equation, that's fine. 8.1.1 says use oxidation numbers for each of the reactants and explain why this reaction is a redox reaction. Okay, now we must understand what is a redox reaction. A redox reaction is a reaction in which there is something that's going to be oxidized and there is something that's going to be reduced. Now remember, oil rig. So oil means oxidation. So OIL, oxidation, is loss of electrons, and RIG, reduction, is gain of electrons. So in this species, or in this reaction rather, something needs to lose electrons and something needs to gain electrons for this to be a redox reaction. So 8.1.1. So I have Mg plus 2HCl gives me MgCl2 plus H2. Now we need to remember our rules when we are writing down oxidation numbers. For example, one of the most important rules is that something on its own, like Mg, will have an oxidation number of 0. So that's going to have an oxidation number of 0. Then Cl, so HCl, it's up to you. You can start with the hydrogen, you can start with the chlorine, doesn't really matter in this case. So chlorine is in group 7 or 17 if you want, and it's going to have an oxidation number of -1. So -1. Then that means the hydrogen, for it to be neutral, should have an oxidation number of +1. Now if I go to my products, I can see here that the Mg, well, let's look at the chlorine then instead. So the chlorine again, group 17 or group 7, whichever you want, and those elements in that group are going to have an oxidation number of -1. However, I have 2 of them, and so if I have 2 of them, I'm going to have a total or a net of -2 here. That means for this compound, for the MgCl2 to be neutral, the Mg must be +2. Now don't get it confused. The Mg is going to have a charge of +2. Each chlorine or each chloride ion is going to have an oxidation number of -1. Since there's 2, the overall will be -2, and that's how it's neutral. And then for H2, remember the rule, if it's diatomic, the oxidation number is 0. So let's examine the reaction and look at how or if the oxidation numbers have changed. So we'll start with the magnesium. So we can see, okay, the magnesium went from 0 to 2 plus. So we can say here, okay, the Mg went from 0, it went to Mg2 plus. Then we can look at the hydrogen. We can say that it went, so the hydrogen went from H plus or 1 plus to H2, which is 0. And so something was oxidized and something was reduced. And so this is a redox reaction. So therefore, it is a redox. Because something was oxidized, something was reduced. So this was oxidized and this was reduced. Now let's take a look at question 8.1.2. 8.1.2 reads, write down the formula of the oxidizing agent in this reaction. Okay, so simply put, the oxidizing agent is the thing that is reduced. So it's a thing that is reduced. So if I look at this reaction, I must figure out first what was reduced. In other words, what gained electrons? So remember, if you gain electrons, since an electron is negatively charged, if you are gaining electrons, you are becoming more negative, right? You are becoming more negative. So you can clearly see that the hydrogen went from 1 to 0, it became more negative, and so the H plus, right, is the oxidizing agent. So we can write here H plus, or you could write the HCl. Doesn't matter, serve the purpose. Now let's take a look at question 8.1.3. So it says, it is observed that dilute hydrochloric acid does not react with copper at 25 degrees Celsius. Explain this observation by referring to the relative strengths of the reducing agents. Okay, now to figure this out, I'm going to just write out the basic reaction here, just so that it's a bit easier for us to see. So the reaction that they are talking about, so 8.1.3, They are saying that copper does not react with dilute hydrochloric acid. So there is no reaction here. And they want to know why. So the first thing I want to do is I want to write out the oxidation numbers of the things that are on the reactant side. So copper, it's on its own, so it's going to have an oxidation number of 0. H is going to be +1 and Cl is going to be -1. And so from here, we're going to be comparing these 3 different ions. So we have the H plus ion, we have the copper 0 ion, or not ion, the copper 0, and we have Cl minus. Now what we do with this from here is we go to our table 4b. For this video, I'm going to be using table 4b, and so the stuff that I'm talking about is going to be applicable to this table. Now what we need to do is we need to find these ions on this table. Now for some of them, there may be more than one option, but in this scenario, no. So let's take a look and try to find this hydrogen ion. So where's H plus? So if you look around, you scour this table, you'll find, okay, there's H plus. The 2H plus 2 electrons gives you H2. Then we need to look for copper 0. So I'm seeing here, this is not copper 0. So there's no copper 0 in this reaction. So I'm not going to highlight it. I'm not going to choose it. However, I could use this one, or I could use this one. Now, right now, we'll just do both. Doesn't really matter. Actually, let me use a different color. So I would use green for copper. So there. Okay. Then I'm going to look for the chloride ion. So Cl minus. I'm looking. There's the Cl minus. Cl minus, let's pick a different color. Let's go with this orange brown color. So there. All right. And now what we want to do is we want to look for where they lie in relation to each other, because that's going to be important. You can see that this table is ordered as you go upward. It's of increasing strength of reducing agents. So in other words, the one that's higher up, the higher up one, is going to be oxidized. The one that's lower down is going to be reduced. Now oxidation is written, for this table, it's written from right to left. Reduction is going to be written from left to right. Now, if a reaction is going to occur, you should be able to draw a diagonal like so, like this, between the ions or the species that's in question. So if you can draw a diagonal like this, that's starting at the top and going bottom left, that joins the species that's here, then the reaction will occur. So let's look at it. So here I have H plus. So H plus is here. So H plus and copper. Can I draw that diagonal? So H plus and copper, the diagonal is going the wrong way. So that reaction is not going to occur. Right? Can I draw the diagonal between copper 0, maybe between these two I could. So copper 0 and Cl minus. No, there's no diagonal. So since there's no diagonal, there's no reaction that's going to occur. Now how do we explain this? Obviously we can't say that there's no diagonal and so there's no reaction. What we are going to say rather is we are going to refer to the position of the ions. So we will say that copper lies lower down than H plus. And since it lies lower down, what does that mean? It means that it's going to be a weaker reducing agent. And since it's a weaker reducing agent, there's no reaction that's going to occur. But for our check, we just need to find the diagonal. That's it. Just look for the diagonal. If there is a diagonal, it's going to happen. If there's no diagonal, it's not going to happen. Okay. Now, 8.1.4. So 8.1.4 says, will dilute nitric acid react with copper? So nitric acid is HNO3. Will it react with copper? That is the question. Will there be a reaction? So again, let's look at the species. So H plus, so that's +1, that's -1, that's 0. Then you have copper 0, and then you have NO3 -1. Now let's look for it. So H plus is already highlighted. Okay, copper is already highlighted, but we need to change this one. We need to change it to NO3 minus. Now, where is NO3 minus? NO3 minus is right here. And so we do our check again. So can I draw a diagonal between the H plus and the Cu, the copper? And so the answer to that is, there's my H plus, there's my copper. Yes, I can draw a diagonal, but it's in the wrong way. So there's not going to be a reaction there. But can I draw a diagonal between the copper and the NO3 minus? Let's see. So here's copper, here's the NO3 minus. There we go. There's my diagonal. And so since there is a diagonal, the answer is going to be yes, there is a reaction. There is going to be a reaction. Now, why? So what's the reason going to be? We can't say that, we can't say obviously there's a diagonal again. So instead what we'll say is we can say that the nitric, or the nitrate in this case, the NO3 minus, right, is lower down, right? Now, since it's lower down, we could say that it is a weaker reducing agent, but better to say, since there is a reaction occurring, we will say that it is a stronger oxidizing agent. Why is this better to say? Because it is implying that it is going to oxidize the copper, right? The copper, the CuO, well, the Cu0 is going to lose electrons because the NO3 minus is going to oxidize it. And so it's better to say that the NO3 minus is lower down and it's a better oxidizing agent. All right? Therefore, copper will be oxidized. Remember, the oxidizing agent is reduced. Okay, now let's move on. Actually, we're not done. Question 8.2. A galvanic cell is represented by the following cell notation. Okay, so there's my cell notation. Write down the balanced net ionic equation for the cell. So when you're doing a net ionic equation, what you need to do is firstly figure out what's being oxidized and what's being reduced. So we can see here that Pb is going to Pb2 plus. So the lead is being oxidized. And the Fe3 plus is going to Fe2 plus. So the Fe, the ion, is being reduced. So we need to write that reaction, but from our table. So let's go ahead and write it. So we want to write on the oxidation reaction. So we're looking for lead. Where's lead? There's lead. Here. So Pb, now remember, if you're writing oxidation, you're going from right to left. So it's going to be Pb going to single arrow Pb2 plus plus 2 electrons. Then we're looking for Fe3 plus going to Fe2 plus. So that's not it. Fe3 plus, where is it? Here we go. Now, since this is reduction, we're going to write it from left to right. So reduction is going to be Fe3 plus 1 electron, giving me Fe2 plus. Now we can't join it up to get a net ion unless we balance the number of electrons. So we can see that here we have 2 and here we have 1. So we multiply everything by 2. And now that the electrons are balanced, we can bring everything down. So my answer is then simply going to be Pb plus 2Fe3 plus. The electrons cancel. And I'm going to get Pb2 plus 2Fe2 plus. And that's my answer. Okay, now let's move on to the next one, 8.2.2. A stronger reducing agent. So they are essentially using something, they're not using lead anymore, they're using something above lead. So let's say they use iron. A stronger reducing agent is now used with the same oxidizing agent under the same conditions. So how will this affect the EMF of the cell? Right? So since, remember, the EMF is, there is a formula that you use to calculate EMF. Right? And the formula you're using to calculate EMF is the E naught of the cell. So let's make a note of it here. The E naught is going to equal the E of reduction minus the E of oxidation. Now, remember, reduction is not changing. That is still staying the same. But if I'm changing the oxidation, so for example, say I change it to iron, I'm going to have minus, and I'm going to have minus 0.44. So actually, I'm going to be adding 0.44. So actually now what's going to happen is, I've said actually 3 times, the E of the cell is going to increase. Okay? So E of the cell would increase. All right, now let's move on. Question 9. So question 9 says a strip of silver is added to a 1 mole per dm cubed solution of PbNO3 at 25 degrees Celsius. Okay. Consider the reaction. By means of a calculation, so calculation, determine whether this reaction is spontaneous or not spontaneous. Now, if they want us to do a calculation, what they want us to do is calculate the E of the cell. Right? If the E of the cell is positive, then it's spontaneous. If the E of the cell is negative, then it's not spontaneous. So let's go ahead. So we need to figure out, so here's the reaction. So it's just a matter of picking the correct equations, okay? So let's go ahead and find these things. So we have here Ag going to Ag2 plus. All right, let's find that. So Ag is Ag here, but that's not the one we're looking for. Ag, where are you? Ag. I can't find it. Ag, oh, sorry, Ag going to Ag plus. Ag going to Ag plus. So there's the reaction we found. We have it here. So Ag going to Ag plus. So that one. And then Pb2 plus going to Pb. So we need to find that one. So Pb2 plus going to Pb. Right? Now, you could do this. You could say, okay, Ag and Pb2 plus are the 2 species that I'm interested in. Can I draw a diagonal between them? So can I draw that diagonal that's going from top right to bottom left? So Ag0 is here, Pb2 plus is here. Can I draw a diagonal? Yes, I can, but the diagonal is going the wrong way. So it's not going to be a spontaneous reaction. But better, unlike the other one, so you know where we did this other one here, they said that would the reaction occur? Will the reaction occur? And this other one where they said the reaction does not occur. So when they say that the reaction does not occur, it means that under those conditions the reaction won't occur. But if you had to add maybe a battery, then the reaction could occur, right? So under those conditions, the reaction won't occur. So just to clarify, so in this case, we can see that the diagonal is in the wrong way. So the reaction normally won't occur, but they want us to show using a calculation. So let's go ahead. We can write that the E of the cell is equal E of reduction minus E of oxidation. So reduction, where's the reduction? What was reduced? Let's check. So PB was reduced. So minus 0.13, then minus, what was oxidation? The Ag was oxidized. So that's minus, and the value there is 0.80. And that gives us an answer of minus 0.93 volts. The negative value tells us that it's not spontaneous. In other words, if you just put those things there, there's not going to be any reaction. But if you connect to the battery, or maybe you change the temperature, then the reaction could occur. Now let's take a look at the last one, question 9.2. The simplified diagram below represents an electrolytic cell. The electrodes are made of carbon. Now, since they are made of carbon, this is going to be the positive electrode. That's going to be the positive cell. That's going to be the negative end of the cell. This is going to be the positive electrode. That's going to be the negative electrode. Okay? Now, let's look at what we have as our electrolyte. We have NaCl. So what is the NaCl going to be made of? So the ions obviously are going to be Na plus, Cl minus, but it's dissolved in water. So we have water here as well. Now, I've already highlighted these in my table 4b. Now what we want to do is let's look at question 9.2.2. The question says, write down the predominant oxidation half reaction that takes place in this cell. So I'm going to go through each one and we're going to see, can that species, can that thing undergo oxidation? Can it lose any electrons? So let's look at the Na plus. So the Na plus is here. Can I write it? Remember, oxidation is written from right to left. Can I write it from right to left? No, I can't. That can't undergo oxidation. Then I look at the H2O. Can the H2O be written from right to left? No, it can't. Then I look at the Cl minus. Can the Cl minus be written from right to left? Yes, it can. So the oxidation half reaction is going to be 2Cl minus goes to, remember, for a half reaction only use a single arrow, Cl2 plus 2 electrons. Okay, next one, write down the names or formulae of the compounds formed at electrode Q. Now, let's firstly understand what's going to happen with the oxidation, right? So the Cl minus, right, since it is a negative, it's going to be attracted here, right? And you're going to have Cl2 forming there. So let me just put the Cl minus so that you can see that negative, the opposite will attract. That means either the Na plus or the H2O will then go here at electrode Q. Now we need to figure out what's going to go there, right? So now, since this was oxidation at this electrode, this must be reduction, right? This must be reduction. And so what we're doing now is we want to look at which one is going to be better, or which one is going to undergo reduction, which one is going to be a better oxidizing agent. So if I look at this, if I look at my two reactions here, or there's my two reactions. I want to see which one will undergo reduction. So remember, the one that's higher up is the one that's going to want to be oxidized. The one that's lower is the one that's going to be reduced. So the one that's going to undergo reduction is going to be the H2O. This here, since it's lower down compared to the Na+, this is the one that's going to undergo reduction. This is going to go this way and you're going to form H2 gas. So they want to know what are the products formed. You're going to form H2 gas hydrogen, and you're going to form your hydroxide ion. And they want to know, explain the answer by referring to the relative strength of the oxidizing agent. Since H2O is lower down, right? H2O is a better oxidizing agent, right? Meaning it's going to be reduced. Going to be reduced. As we can see, it was lower down, it's going to be reduced.